Okay, so let's today talk about the pimple form. Okay, so let me open the readme file. So in the pimple form we try to talk about laminar as well as turbulent flow, and in the turbulent flow we stick to the runs modeling only. Okay, so this is the few things we try to look at today about the pimple form. So first, before we go towards exactly the test cases, let's look at the its source code where it is located. So for that we have to go to the area where OpenFOAM is installed. Okay, so OpenFOAM 3.0x solvers incompressible and the pimple form, and open this pimpleform.c file. So let's read the description. Large time step transient solver for incompressible flow using pimple, merge piezo and simple algo. Okay, and turbulence modeling wise laminar, runs and LES. Okay, as well as runtime selectable MRF FV options and explicit porosity that is possible with the help of this pimple form. But important aspect is merging of piezo and simple in the pimple form. What it mean? It means that when we look at the piezo algorithm, okay, we have a chance to iterate more number of time or do the correction multiple time. Okay, but that is not available in the simple form. But what available in simple form is the under relaxation parameter. So that concept of under relaxation parameter is adapted from the simple form, and this multiple correction from pimple. So when we merge pimple and simple, it happened to be the pimple type of the algorithm, and in the pimple at a one particular time step we can go for multiple time of predictor and corrector type of the things. Okay, so that we come to know through our test case. So this is first introduction about the pimple form. So let's go towards our working area where we want to explore the certain tutorials. So pimple form, let's go to the laminar test case and 2D circular cylinder. Okay, same case what we run with the piezo algorithm, similar type of the case we try to run with this pimple algorithm. But before we go towards its running, let's look at few entries. So here same way laminar is if we want to go with the runs, then select the runs in the simulation type. LES, then select the LES. If we want to go for DNS, then stick to the laminar only. Okay, and different class of models is available. Okay, then in the transport property we require only the kinetic viscosity, so that is also available here. Along with that, few changes we going to observe in the control dict file as well as in the FV solution. So let's first look at control dict file. Control application is pimple. Okay, so we can change different delta t and try to look at the flow, or we can go with the adjustable runtime. Okay, so this is the very important concept in the pimple algorithm that is not available with the piezo algorithm. Okay, so with the help of the pimple algorithm we have leverage to fix the current number that is here. Okay, so we say maximum current number is 1, and as based on this maximum current number it immediately try to calculate the delta t. Okay, from the formula of current number, and based on that one can easily or quickly check what is the delta t required. So if I give you the very quick idea about how it is calculated, so let's go towards our simple user manual. Okay, and here it is available how one can calculate the current number. Okay, so yeah, here, so look, current number is nothing but delta t. U is the free stream velocity or magnitude of velocity. Okay, at a particular cell, and delta x. Okay, so normally how it goes, at each cell they try to calculate this current number. Okay, so if we fix the delta t, then for each cell we have to look at the localized magnitude of velocity, delta x, that is the cell size of that particular cell, and the whatever the delta t we fix, based on that we fix the current, based on that we calculate the current number. But here what we are doing, we are fixing the current number so that we can find out what's supposed to be the delta t. Okay, so as the, let's say flow is progressing and we find in some very tiny small passage the magnitude is increasing. So when the magnitude is increasing, immediately what supposed to happen, to fix the current number, okay, we have to change the delta t appropriately. Okay, so like that way we can stabilize the flow even for a highly unsteady and the turbulent phenomena is occurring. Then also no problem, if we fix the current number, immediately we can switch to adjustable time step type of the things. Okay, so that is what we are doing here. We are allowing the simulation to adjust the delta t. Okay, so it is here, adjustable time step is yes. Then we have a two control, either we go with the maximum current number, okay, or maximum delta t. Okay, so whatever the delta t for this current number, it not going to go beyond this maximum delta t. Okay, sometime it is very important if we are working with, let's say, turbulent flow, and we require the definite flow feature in within the some very small tiny time step. Okay, so at that point of time we can go with the fixing the maximum current number to, let's say, it is always good if we go with the less than 1. Okay, and then we also give the small value of the maximum delta t. Look, sometime in the turbulent phenomena, how normally people look at it something like this way. Even though we have a larger time step possibility, then also we cannot go with a very large time step. Why? Because when we go towards a very large time step, so we are losing the physical information in between two consecutive time step. Okay, so that information, let's say, is very important to find out the very nice statistics. So in that regard, even though we have a leverage to go up to current number 1, but we cannot go till current number 1, because when we go, let's say, current number 1, then maybe the maximum delta t reach, let's say, 0.1 or so, but 0.1 is a very very large delta t to capture a very nice physics. So normally when people work with the turbulent flow, so this value supposed to be 10 to the power minus 3. Okay, and the let current number be something like 1, and so always we restrict that, say, maximum delta t cannot go beyond this particular value. Okay, so that is how normally one has to take into account. Okay, so let's right now let it be a 1, because we are working with the laminar flow and current number is, let it set as a 1. So when we say adjustable runtime equal to yes, okay, at that point of time time step equal to yes, we can go with the right control as this adjustable runtime and writing interval. For every 0.1 second we going to write the data. Okay, along with this we have all that probe information, incoming mass flow rate informations, okay, outflow informations, and averaging concept is also be there, but I am switching off this part. Okay, later on when we look at the probe and we satisfy with the let's say development of the flow, after that we try to switch on this portion. Okay, then all force calculations available to calculate the CDCL and all the coefficients, okay, and max min within the entire domain. So these few entries is available. Along with that, schemes, so we are going with the backward type of the schemes. Okay, and all entry are almost same, but here you observe certain difference. Okay, so solver wise is okay, but if you look at here we have a piezo entry, okay, sorry, pimple entry, okay, and momentum corrector. If we enable it, it will go at a final correction stage. Okay, or sometime it is required for, let's say, when we are working with buoyancy driven flow or that type of the flow, at that time normally we try to look at this momentum predictor corrector. Yes, okay. One more thing, if this is n, look, in the piezo we have these two entry only, and this is for our taking care of pressure reference value, but this two entry is exactly same what we observe in the piezo algorithm. Okay, over that we have one more entry is called n outer corrector. Okay, so if you keep n outer corrector equal to 1, okay, and you don't specify this relaxation parameter, okay, then algorithm wise is almost like a piezo algorithm. Okay, so if you want to work with the piezo with the relaxation, then put it 1 and keep it relaxation. This pimple algo exactly work as a piezo type of the algorithm. Okay, so please understand that way. This is outer corrector, Okay, so an outer character if is 1, then it's not going to go for multiple time of predictor step. Okay, so that is how one can compare the piezo and pimple type of the algorithm. Along with that, we have a relaxation parameter. That is, this concept is coming from the simple type of the algorithm, where we have leverage to under relax the certain parameter to stabilize the flow. Okay, and because of this relaxation applicability as well as number of outer character, you can go for a larger number of the delta t as well. That's why it is always called large time step type of the algorithm. So if when we, let's say we work with the piezo type of the algorithm for large Reynolds number class of the flows, at that time maybe we require the smaller delta t, but when we switched from piezo to pimple, we have a flexibility to choose a larger delta t. That means we can fix the current number, let's say 1. Okay, but in case of piezo algorithm, we cannot go till the 1 as a current number. Okay, so why that's supposed to be? Because we have a flexibility to choose the appropriate relaxation parameter that will allow the flow to stabilize little bit better way. Okay, so this is few more entry you can see as compared to the pimple algorithm, that is the relaxation parameter. Same thing is coming from the simple type of the algo, and in the pimple bracket or in the pimple area, you can see the n outer character. This one more entry is available here. Okay, so all other are our normal setting. Okay, so this is few changes you observe here. Okay, so let's go back to our regular files. Okay, so we going to run for r equal to 250. So please check the transport property. It is appropriate. Yes, it is appropriate, so no problem. So let's start these simulations. For that, go to the terminal, go to that particular area. Okay, source the our allies. So our environment is ready to go. Now let's execute step by step. So first clean the tutorial, block mesh, check the mesh. Okay, so how many element we have? We have a total 12k. Okay, let's go for visualization how the mesh and everything look like. So this is our domain, flow over circular cylinder, and this is the mesh what you are observing. Okay, so this is few things we can observe from here. Okay, so let's go to the readme file again. Few things I kept more, that is renumbering of the our entire matrix. Okay, so let's look at what exactly this renumbering going to do. So look, first understand something like this way. When we discretize, okay, and we are working with the sparse type of the matrix. Okay, sparse matrix, that means for each of the single row at a diagonal entry we have, and we have a certain off diagonal entry, but that off diagonal entry is scattered based on our neighboring cell. That means, let's say when you look at any of the parent cell, it's not necessary the cell number 1 has a neighbor of 1 2 3 4 5. No, but cell number 1 has a neighbor maybe 1000, 2000, 10,000, any of this number. I'm talking about the cell global index number. Okay, so let's say we are at the cell number 50, and if we want to discretize, we require a certain entry from all the neighbors. Okay, so it's not necessary the cell number 50 has a neighbor of 49, 48, 51, 52. No, it is possible if you work with the, let's say, finite difference class of the problem, where we go with the ijk indices and it is always in the banded type of the matrix. Okay, but here we dealing with the unstructured type of the mesh. Okay, along with the let's say hybrid mesh and any class of the mesh, so we cannot go with that. So we require the connectivity index in and if you look at the connectivity index, it normally goes something like whatever the cell we are talking, let's say cell number 50, not it neighbor maybe 100, few thousands, anything is possible. So whatever its neighbor number in the global matrix at that particular column of that particular row, that coefficient is going to be store. Okay, that is normal when we discretize the our equations, and before we go for solution, if we go to rearrange that particular numbering, so what it allow us to do, it allow us to reduce the bandwidth. Okay, so let's execute this one command. So look, so previously our bandwidth was that much. Okay, and now after that our bandwidth is very low. So how it going to benefit it? If our bandwidth is very low, or very all the coefficient in each line is clustered near the diagonal entries, okay, then when we try to take the data, okay, at that point of time, maybe that whatever the bandwidth we are talking, it may be fit within our available L2 cache memory. Okay, and if it going to fit within our L2 cache memory, we can speed up our calculations. Okay, so it will help us to simulate much faster. So you're not going to observe this change for a very this small type of the mesh size, but when we talk about some millions of mesh, at that point of time, this renumbering really affect the calculations. Okay, because when we talk about millions size of mesh, so maybe the cell number once has a neighbor something like after a 5, 6, 10 lakhs of element. Okay, so in that regard, when we talk about this rearranging the bandwidth, it helps a lot. Okay, so for this tiny case also, if you see, our bandwidth boiled down to 130. So it is a pretty good way to rearrange the mesh. So what it going to do, it try to rearrange the mesh such a way that our bandwidth going to be very narrow. So bandwidth going to be very narrow. That means what going to happen, that along the diagonal entries, all the other coefficient going to be clustered very near to that. Okay, so that is what one can see. Now let's run this case with our regular way of running the case. So simulation is going on. Okay, let's check the entries, so at least we have idea. Okay, so look, we fix the maximum Quadrant number equal to 1, but it's not going to reach immediately 1. Okay, please understand, it slowly try to go towards the whatever you specify the maximum Quadrant number, and this delta t, whatever we going to get, it never going to go beyond 0.1. What it mean? It mean this, whatever the delta t after the fixing the Quadrant number we going to get, it never go beyond 0.1, because it going beyond 0.1, we restrict maximum delta t supposed to be 0.1 only. Okay, so like that way we can fix the maximum delta t. Okay, and this is the Quadrant number. Based on this Quadrant number, okay, this delta t is changing. Okay, so look, every place you will see the change in Quadrant number. Okay, and based on that we are changing the delta t. Okay, so let's look at here. Now it's still going something like Quadrant number equal to 0.59 or so. Okay, so that is how we check the flexibility in choosing the delta t. Okay, so let's first look at the paraform, how the simulation is progressing. Okay. So simulation is started. Okay, slowly we're going to observe the vertex shading out of it. Okay, but it going to take a time. So meanwhile, just look at the GNU plot. Okay, and check the script how the CDCL is progressing. Okay, so CD reach up to there, and CL is yet to start fluctuating. Okay, let's observe how the residuals are falling. For that, let's look at this PyForm utility. Sorry. so it shows the residuals falls. Okay, so slowly it's going to fall. Okay, so it's going to take time, so let's wait till it start going towards unsteady nature of the simulations. Okay, so one few more thing, please understand, when we are working with this transient or unsteady flow, okay, in the steady state calculation, what going to happen, the residuals fall till 10 to the power minus 6 or so. But when we talk about the transient calculations, okay, so sometime it is very demanding if we asking the simulation to reach till 10 to the power minus 5 or so. Okay, so normally it is not the good way to start the transient calculations. Okay, so normally transient calculation, you give the residuals something like 10 to the power 4 at the max, okay, for u, v, p and w, and then let the flow to develop. Okay, what it means let the flow to develop is something like this way: over a number of time step, over a certain flow time, okay, the flow going to develop towards its actual physical natures. Okay, that is what we are observing from this particular entry. Something wrong with that particular it's stuck. Okay, so I don't know why. Let me open one more and let's say go towards GNU plot. Okay, so what I mean to say is something like this way: if you see the CDCL value, okay, it's slowly developing and finally try to reach the final development stage, and we are normally interested after it reach the development stage. Okay, so at the beginning, even though our residual don't fall 10 to the power 4, 5, 6, no worry. Okay, so this is very simple test case, so not a issue. But when we are working with very complex physics type of test case with the turbulent unable and let's say LES type of the calculation or DNS type of the calculation, then don't select the residuals fall 10 to the power let's say something like minus 4 or minus 6 or something. Okay, don't expect that that going to fall up to that. Okay, no, it is not going to fall up to that level. Okay, so one has to look at the transient calculation differently as compared to the steady state calculation. In the steady state calculation, residual is going to fall 10 to the power minus 6 or so, but in case of the transient, that is not the correct way to look at the simulations. Okay, so normally when you talk about the transient calculation, try to put certain props, okay, and either props or some other marker. Okay, or if you are talking about heat transfer, then any of the wall, try to look at the average Nusselt number. Inside the domain, try to keep some probe on, and on that try to look at the temperature. Okay, or you can if fluid flow and if it external aerodynamic type of the case, then CL and CD value is the perfect marker and tell us exactly what is happening with the flow development. Okay, so this is all things one has to take into account as compared to the residuals. Okay, so sometimes residuals is misleading when we talk about the transient calculation, and if we are expecting, let's say, residuals fall 10 to the power minus 4 or so, no, that is not the correct way. In couple of transient calculation, I observe even residuals fall 10 to the power minus 2 only. Okay, why? Because immediately if there is a very heavy turbulent flow, then few turbulent structure are emerging, merging, interacting, bursting, so many phenomena happening, and because of that we cannot expect that residuals fall 10 to the power minus 5, minus 6. No, that goes a wrong way to look at the simulations. Okay, so when you are working with the transient and the turbulent type of the cases, then only rely on probe or some other marker. Okay, and based on that you judge your simulations. Okay, one more thing, when we talk about the let's say with this pimple type of the calculations, okay, and we are talking about this flow over circular cylinder. This is very low RE case. Let's say you want to simulate with very large RE case for flow over a circular cylinder. At that time we are interested to extract some statistics. Okay, so when we are interested to extract some statistic, so make sure that even though we say that our current number is 0.1, sorry 1 or so, but make sure this delta t don't this delta t will be something like 10 to the power minus 3 or so. Okay, it is very very important to get a for getting a very nice statistic. Okay, so this is how you can see the unsteady type of the calculations. Okay, now what I want from your side is following thing. You already run the case, similar case with the pimple form. Okay, now you are running the same case with the you already running the same case with the piezo form. Now we are running with the pimple form. Okay, later on you try to compare the CL and CD plot 1 to 1 for piezo based algorithm and pimple based algorithm. Try to get a feeling either both started unsteadiness at the same time or at the different time. So that is one exercise I want from your side. Similar line, we also kept a probes, okay, for at a 5 different locations in the this test case as well as in the piezo test case. You try to compare the development of flow physics, okay, at a so and so particular probe for piezo and pimple based algorithm, and try to compare the result and try to get a feeling which is developing much faster or which is much slower. Okay, that is one thing. You one can do very quick exercise that give you the idea how the piezo and pimple is varying as far as the flow development is concerned. Okay, then you run both the simulation till it reach the dynamic nature. That means we have to run something like 80 or 90 second, and then we going to start this averaging. Okay, so you start averaging for piezo and pimple, okay, based on when they reach the its dynamic nature. Okay, so from the piezo case we observed that it reached dynamic nature after something like 80 or 90 second, but we don't know right now with the pimple when we going to achieve that state. Okay, so try to look at that aspect as well. Okay, so when it reach the dynamic nature, you start averaging by opening this two commented part. Okay, and then average till it mature the mean quantities. Okay, and then compare the mean quantities, that means x component of velocity and y component of velocity at a different location after the cylinder between piezo and the pimple algorithm. Okay, mean quantities try to check. Okay, and get a feeling that are you achieving some mean quantity is also in similar line or there is a difference in between. Okay, so few things one can do with this class of calculation. Normally when people do this flow over a circular cylinder class of the calculation, they are interested to find out the Strohal number. Okay, so you can also find out the Strohal number from this particular test case. So for that you have to wait till flow become fully developed. Okay, so when the flow become developed, that means when the consecutive peak value is not changing. Okay, till if you see this peak value and this peak value is continuously changing, it is something like 0.15 and this almost reach 0.25. okay, so when this consecutive peak value is not changing, we have to take that peak. Okay, and that peak difference in time we will find out. Okay, so this peak and this peak, what is the time difference? So if we have a time difference, inverse of time difference give us the frequency. Okay, so let's say inverse of time difference give us the frequency. So frequency into length scale divided by velocity. Okay, incoming velocity, that give you the Strohal number, and normally people try to compare this Strohal number with the open literature. Okay, so you also try to look at this Strohal number for, let's say, r equal to 250. For our case, the length scale is diameter of the cylinder for and diameter equal to 1, and incoming velocity what I set is 1. Okay, so that means the Strohal number whatever we want to calculate is nothing but directly the frequency, and frequency we are going to get by checking the difference in time between two consecutive peak. So inverse of that time it's the frequency, and with the help of that we can calculate the Strohal number. Okay, so you also try to check the Strohal number between this piezo and pimple algorithm. Okay, and get a feeling either you are getting the same Strohal number or not. Okay, are the flow is developing in the similar line when we are going from piezo to pimple algorithm or not. Okay, more or like for this class of the case you will not find much difference. Okay, but when we talk about the highly turbulent flow, okay, at that point of time you see a very large difference in between the piezo and pimple development. In the large difference in that way, I am saying that with the pimple you have leverage to go towards the very large delta t. That is not possible with the piezo. So maybe piezo will take a longer time, absolute CPU time I'm talking. Okay, why? Because we in that case we have to go towards very low delta t. Okay, and simulation time requirement is going to be too heavy at that point of time. So other exercise one, if we really want to get a feeling about the both the algorithm, then try to run the similar case flow over a circular cylinder. Okay, but this time go with, let's say, very large array, let's say something like 10,000 or so, and don't go towards runs modeling. In the laminar activation, go with a very fine mesh. Okay, refine the mesh. Right now we have only hardly 12 k element, but you supposed to go something like 250k or that range of mesh. Near wall spacing something like 10 to the power minus 4 or so. Okay, and with that near wall spacing and with that particular let's say mesh size, try to run with the piezo and pimple case for a very large array, and at that point of time try to compare all the probes and all the statistics and so many things. Okay, so that is a very very good exercise when we are dealing with the transient type of calculations. Okay, so now if you see our flow development, this CDCL this is CL value. So if you see the consecutive peak, it's almost reaching the dynamic nature. So same thing we observe for piezo algo as well, but that is something like after 80 or so, if I remember correctly. Okay, but I am better you compare one-to-one plotting. Okay, so first go finish the simulation for pimple, finish the simulation for piezo, and then assemble both the plots with the help of GNU plots. Okay, so the same script you have to just edit. So whatever the script right now I gave you. Okay, so in the script we have a CDCL. Okay, so in place of this one you can put a 2 lines, comma and another line. Okay, and like that way you can at a time open the multiple like this way, sorry, at a time you can open multiple lines like this way. So here we have one line for one probe continuously, second line, third line. In the similar line, one line for one CD that is coming from piezo algorithm and another line from pimple algorithm, and you have one-to-one comparison in this particular snapshot. Okay, so that gives you the idea how the progress of simulation is going on when we are switching from piezo to pimple class of calculations. Okay, so let's now go towards paraFOAM and check how exactly the unsteady nature is built up. Okay, so let's first directly go to the last file. Okay, so fine, let's look at the animations. Okay, so slowly it's building up. Okay, let's put some annotation, few more alphabetic, and there is a one very good annotation is available. Okay, time filter. Okay, so you can apply the time filter. It give you the idea how exactly with the time flow field is behaving. So this is sometime very handy tool to put inside the any of the animations. Okay, so it give exactly the viewer idea when the unsteadiness or the vertex shading is started. Okay, so slowly it building up, and then finally it going to oscillate, and finally we get a vertex shading. Okay, So each algo has its different nature. Okay, so when you compare the result between piezo and pimple, you come to know exactly how it's vary. Okay, so I say it is a very good exercise, okay, for the beginner to compare the result between piezo and pimple result. Okay, so this is how we are seeing the vertex start departing from top and bottom side. Okay, so this is very nice vertex shading one can observe. Okay, so this is few things I suggest try to check with this particular class of test case. Okay, try to look at the probes as well, okay, with our particular script. So let me we have a name of plot probes. Okay, we didn't clean the case. Okay, so that's why it's showing the error. So I already showed you how you can create this u final. Okay, so try to work with that. That means it is available few things in the, okay, that entry I didn't kept here, but if you want that exactly the file, so you have to go towards our previous tutorial number 4, piezo laminar, okay, flow over a circular cylinder, and maybe, okay, I exactly where we kept this particular file, let me find out. Runs, okay, omega, yeah, maybe here in this particular place you will see this few lines. Let me copy and kept for your same place. Okay, so it will be handy. Okay, so with the help of this two command we can clean the probe area, and then we can look at the exactly the post processing for probe files. Okay, so let quickly do that, so at least you have idea. I am switching off the simulations. Okay, post processing we require the probe informations. Okay, 0 folder here. Now we have this two command to execute. Okay, so we go towards one command, okay, and then we use another command. Okay, so with this we able to clean all the probe informations. Okay, and now look, this is the probe, how it's look like. Okay, so what I suggesting, you compare the probe for a single location from piezo and pimple. Okay, and try to create a very nice plots out of it. Okay, so this is how one can check the probes. Okay, so now I think you understand how to look at the few entries in the GNU plot with the help of certain script files. Okay, so this is about the laminar test case.